In the last program, we looked at the sediments and the surface volcanic rocks around the Red Sea and concluded that all the evidence indicates that the Red Sea has formed in the last 30 million years. And the near coast-to-coast fit is very reasonable. But how and why did it all happen? To answer that question, we need to look at the Earth beneath the Red Sea itself. There is a variety of good evidence to suggest that all the marine area in the southern Red Sea is underlain by oceanic crust. Glomar Challenger has drilled across here in the deep sea drilling project, and their cores have penetrated thick evaporites. Certainly, the axial trough is underlain by oceanic crusts, for oceanic basalts have been dredged from the floor. And these basalts, together with those from volcanic islands, are comparable in all ways to the basalts of major oceans. Furthermore, linear magnetic anomalies have been detected over the axial trough, and these, together with other geophysical evidence, such as heat flow and earthquake foci, leave no doubt at all that an active constructive margin underlies the axis of the Red Sea median trough. And relating the linear magnetic anomalies to the magnetic polarity reversal timescale suggests that the spreading rate was just under 1 centimeter per flank per year. Now, as the Red Sea around here is about 400 kilometers across, it should at this rate take about 20 million years for the Red Sea to form by seafloor spreading. So even more convincing in this respect is that just here in southwest Saudi Arabia, right on the coastline, there's an outcrop of oceanic basalt that dates at 21.5 million years. So it all fits very nicely. All the Red Sea is underlain by oceanic crust formed at a median constructive margin with a constant spreading rate of about 1 centimeter per flank per year for the last 20 million years. Now, could it all be that simple?
When we look at the geophysical evidence, which tells us what goes on beneath the Red Sea floor, we find that it paints a rather more complicated picture. In general, the Red Sea is rather poorly covered by geophysical data, but we're fortunate in having one complete coast-to-coast profile across the central Red Sea from the Sudan here to Saudi Arabia. The bathymetry along this profile is typical of much of the Red Sea. In the center here we have the deep axial trough descending to depths of more than 2.5 kilometers. And flanking this we have shallow marginal shelves which are underlain by many kilometers of evaporite. The aeromagnetic survey flown across this area shows some interesting features. The peaks in this profile are called positive anomalies, and the troughs here are called negative anomalies. Now, over the axis itself, we have these very large magnetic anomalies, which extend out beyond the deep water axis. We'll call these type 1 anomalies. Flanking these on both sides, we have smaller, smoother anomalies, which extend all the way to the coastline. We'll call these type 2 anomalies. And onshore again, we have these even smaller anomalies, which are typical of continental crust. Now, as you notice, these type 2 anomalies happen to coincide with the thick evaporite sequences on the flanks. However, we know that magnetic anomalies are not attenuated by evaporites, and so the difference between the type 2 and the type 1 anomalies is not due just to this and must have some other cause. Now, this profile only gives us a picture of the magnetic anomaly pattern along one transect of the Red Sea. When we look at this area in plan view, we see that the magnetic anomalies form linear features running parallel to the Red Sea axis. In this case, we show the positive anomalies as black lines and negative anomalies as white lines. There are 1 or 2 short anomalies which run at right angles to the axis, but we think these are just associated with transform faults. Whenever we see magnetic lineations like these running parallel to a spreading center, it suggests we're dealing with seafloor spreading. In fact, this was one of the first areas where Professor Fred Vine identified magnetic anomalies associated with seafloor spreading. And he showed that our type 1 anomalies here were caused by a phase of seafloor spreading at about 1 centimetre per year for the last 4 million years. And our later work has showed that this is pretty much the case. What about these type 2 anomalies then? Have they been caused by seafloor spreading? And if so, when? Now Ian has made the simple and obvious suggestion that they've been caused by continuous seafloor spreading for the past 20 million years. Now to test this idea, I've compared the observed profile, that's the blue line, with a computer simulation based upon the assumption that continuous spreading has occurred. That's the white line. The type 1 anomalies fit very well for the last 4 million years, but look at the older anomalies. I think you'll agree they don't fit very well at all. Now the area we've been talking about in the Red Sea is here, and our profile ran from the Sudan across to Saudi Arabia. But we've also done some work further to the southeast here in the Gulf of Aden. And the data we collected in the Gulf of Aden can help us solve our problem in the Red Sea. Now the seafloor spreading picture here is rather less complicated, partly because we've got more data to work with, but secondly because the bathymetry isn't obscured by the evaporites. Now it's quite legitimate to use data from the Gulf of Aden to make inferences about the Red Sea, because you'll recall from the plate tectonics of the region that the Red Sea and the Gulf of Aden have to form together as the Arabian plate here moves away from Nubia and Somalia. My interpretation in the Gulf of Aden shows that the type 1 anomalies, which are associated with the rugged bottom topography along the center of the Gulf of Aden, have been formed by seafloor spreading in the last 5 million years. The type 2 anomalies, which are found over the smoother margins, appear to have been formed by an earlier phase of spreading, which began 30 million years ago and lasted until about 15 million years ago. These two different types of anomalies suggest that seafloor spreading must have stopped for 10 million years between 15 and 5 million years ago, when the process started up again, producing the large type 1 anomalies. The synthetic anomalies, which I've generated based on this two-stage spreading model, match what we observed very well. Will this two-stage model solve our problem in the Red Sea? As you remember, the white line here represents our original synthetic model based on the assumption of continuous spreading in the Red Sea basin. And this one is based on my new two-phase model. I think you'll agree it's a big improvement. So, I believe from the geophysical evidence that a two-phase spreading model best explains this observed profile.
Well, Peter, your evidence for the latest phase of spreading is pretty convincing, your type 1 anomalies. But I'm not quite so happy about your 10 million year hiatus before that. Being rude to geophysicists is a favorite geological pastime. And being deliberately provoking, I could say that all Peter's computer was doing was to compare two sets of squiggles. Still, we accept these observed and synthetic anomaly comparisons elsewhere. So why not here? You remember Peter's emphasis that Arabia acted as a rigid plate. Then, as Arabia moved, the Red Sea and the Gulf of Aden have to have had similar histories. But so too must the Afar triangle. I've been to Afar, and very many years of geological research have been done there, and they suggest a very different volcanological history to Peter's proposed two-stage model. Geologists working in Afar have shown that there were three quite distinct phases of volcanic activity, each separated by short periods of quiescence. On this histogram, the age of the rocks is plotted against the number of rocks dated. Notice there's an early phase between 27 and 19 million years, then another between 16 and 11 million years, and the last one between 8 million years and the present time. So, Peter, why not 3 or perhaps even more phases of spreading?
Okay, Ian, but all that histogram shows is the number of surface samples of rock plotted against age. How can you be sure that that's representative of the actual episodes of volcanic activity?
That's fair comment, Peter, but over 150 specimens were collected and dated, and tilt block tectonics expose older volcanic horizons. The geologists concerned were experienced, and they collect the specimens specifically to date the sequence. So I think the results we have here have to be accepted at their face value, and they are at least semi-quantitatively significant. So what about a multiple phase spreading model for the Red Sea?
Well, I have run this 3-stage model which Ian proposes based on the episodes of volcanic activity. Why don't we have a look at it? Well, this is my proposed 2-phase model, which you've already seen. Remembering it's the white line, which is a synthetic anomaly. And this is the computer synthesis of Ian's multiple phase spreading model. Quite honestly, Ian, I think it's worse rather than better.
Okay, this could go on forever. Let's agree to differ on the earlier episode or episodes of spreading, and agree that the floor of the axial trough has been formed in the last 4 to 5 million years, and that the rest of the Red Sea marine area is floored by oceanic crust produced in the last 20 or perhaps 30 million years. What we should be asking now is how and why did it all happen? There's no doubt that Africa and Arabia were one prior to 30 million years ago, and before that time, as far as we can tell, there was no indication that anything was about to happen. At that time, 30 million years ago, the nearest constructive margins were down here in the Atlantic and over here in the Indian Ocean, and there was a major destructive margin between Africa and Arabia and Eurasia, and fold mountains were being formed along the southern margin of Asia and Europe. So why did the split occur here when and where it did? Well, first, the part of the continent that split is relatively young, and intuitively it would seem to be a far better candidate for splitting than the older cratons, which are underlain by 400 kilometers of old, cold, dense upper mantle. Second, the earliest signs of activity were the eruption of vast quantities of basalts in the Yemen and the Ethiopian trap series, and here this means that magma must have been produced in the underlying upper mantle. Third and last, it seems significant that at about this time, say 40 million years ago, the combined Africa-Arabia plate, which had been moving northeastwards, slowed down and began to stop, possibly because it impinged upon the other major continent, Eurasia, to the north. Now, there's very good evidence that heat flow from the mantle is uneven, and when the African plate stopped, it's possible that zones of anomalous mantle formed above the areas of high heat flow and beneath the crust, the grey area in this cross-section. The production of low-density mantle requires an increase in volume, and this can best be accomplished by vertical uplift on a regional scale. Within the anomalous mantle, discrete pockets of magma developed, from which the trap series basalts were erupted, starting 30 million years ago. Eruptions continued intermittently for the next 10 million years, by which time most of what is now Ethiopia and Yemen were covered by basalts up to 3 kilometers thick. When this volcanic phase stopped, the weight of these lavas caused the crust to sag into a shallow basin. When volcanic activity restarted about 20 million years ago, it was concentrated along the line of the Proto-Red Sea, and the Arabian plate began to move away from Africa as basalts formed along the Red Sea axis. This was the beginning of the ocean floor, and as it developed, the Proto-Red Sea began to take on a linear form. The flanks rose, the seawater occupied the trough, and at times the basin was isolated and evaporites were deposited. Fine, the lines of weakness are there, and the area is underlain by magma-lubricated mantle. But why should these develop into the Red Sea and Gulf of Aden new constructive plate margins? It's speculation, but I think that by 20 million years ago, the plate tectonic system got stuck here in Europe, where Africa and Europe had collided. The Tethyan sediments were compressed into the Alps. Further to the east, the Arabian plate still had some distance to go. Ocean still existed between the two plates, and subduction continued. Now, with subduction, the cold, down-going oceanic plate is denser than its surroundings, and so it descends under its own weight. This is called the sinker effect, and some earth scientists believe that the pull it exerts on the rest of the plate is a main factor in seafloor spreading. Now, if this bit of oceanic crust was attached to the Arabian plate, then could this have pulled the Red Sea open? With lines of weakness along the Proto-Red Sea and the Gulf of Aden, all that has to happen is for the northern section to split and lateral movement to take place along tectonic tramlines. And these tramlines can be recognized today as the Jordan-Aqaba Fault to the north of the Red Sea and the Owen Fracture Zone to the southeast in the Indian Ocean. In this model, the Red Sea up to the line of the Aqaba Fault is floored mainly by new ocean crust. The process continues as the Red Sea widens, and the end will only come when Arabia moves towards Asia and then finally stops. Well, we've looked at a lot of evidence from the Red Sea and put forward what I believe to be a good working hypothesis to explain why it's there. But can we invoke the mechanism that produced the Red Sea to explain why other, older oceans were formed?
The older oceans which we know most about are the North and South Atlantic and the Indian Ocean, all of which came into existence in the last 200 million years. Let's examine the working hypothesis for the Red Sea and see to what extent it can be applied to these older oceans. The hypothesis has three elements I want to examine. First of all, there's the suggestion that the place where a continent breaks may be controlled by the location of younger, weaker areas of crust. Secondly, there's the possible sinker effect, as a cold, subducted slab may assist in pulling apart the plate which it's attached to. Thirdly, there's the possibility of lithospheric thinning by heat from below. Now, as to the first of these factors, we have abundant evidence that it is indeed a most important aspect of the breakup of continents. Consider the North Atlantic. Now, in this region, we have the lower Paleozoic Caledonian mountain chain running here, and the upper Paleozoic Hercynian chain running through here and over here, running between the older Precambrian nuclei of the Canadian Shield, the West African Shield, and the Baltic Shield. When the North Atlantic opened, it did so along a rather irregular line, which was clearly controlled by the disposition of these younger orogenic belts, particularly the Caledonides. So I think there's no real doubt that this is a very important factor in the whole process. Now let's move to the southern hemisphere and look at some aspects of the breakup of Gondwanaland. This reconstruction shows how things looked approximately at the end of the Triassic period about 200 million years ago, when the continents were more or less clustered round the South Pole, and the oceanic areas surrounded Gondwanaland, which then proceeded to break up by the outward dispersal of its various parts. Any subduction which was going on immediately before breakup was along this marginal zone, and it consisted of the neighboring oceanic plates diving underneath Gondwanaland. Under these circumstances, any cold subducted slabs, if they were going to exert the sinker effect, could only have done so by splitting up the oceanic plates and not the continental one. we have here the problem of trying to initiate the breakup of this large continental mass, and clearly we have to look for some other mechanism. Something underneath Gondwana land, one presumes, has to be taking place, and some sort of mantle uprise is indicated. Earlier in the program, it was mentioned that if a continent stands still for any length of time, it's possible that the mantle beneath it begins to warm up. Now, it is true, and paleomagnetic evidence shows this, that Gondwana land had been more or less stationary for some 300 to 400 million years before it began to fragment. So it's possible that subcontinental heating could have contributed considerably to the way it began to break up. But if this is so, this is a very much longer period of time than the 20 million years of standing still which was postulated for the Red Sea area during the Tertiary. If subcontinental warming up is applicable in both cases, then certainly the time scale was extremely different in the two cases. Is there anything else we could think of which might be a relevant mechanism? I mentioned earlier on the subduction which may have been taking place along the margins of Gondwana land. The material which is subducted in these cases is oceanic lithosphere, which contains mantle peridotite depleted in basaltic constituents which have earlier gone to form the basalts of the mid-ocean ridges at spreading centres. The depleted peridotite in the subducted slab, rather remarkably, and this is not intuitively obvious, actually becomes buoyant relative to normal mantle when it's warmed up after subduction. Now, it's possible in the case we're talking about that if this had been going on for a very long period of time and all the material which was subducted underneath Gondwana land was not immediately cycled back to mid-ocean ridges, but remained and accumulated beneath Gondwana land, that rising masses of depleted, buoyant mantle material might have driven up into the overlying lithosphere, transferred heat to it, and begun to stretch it and help the pieces to break apart. Well, what can we conclude from all this? We have, I think, established that the disposition of lines of weakness in the existing crust is one of the very important features controlling continental breakup. The sinker mechanism is perhaps important in some cases, but doesn't appear to be important in all of them. Then the mantle instability that seems to be required, possibly it is purely thermal, as in the case of the Red Sea hypothesis, or possibly, as in the case I've just discussed, it may have its origins in compositional differences in the mantle. But during the course of the program, you may have noticed that as soon as the causative mechanisms of the Red Sea itself were discussed, evidence was immediately brought in from much larger areas. This was inevitable, and it means that by itself the study of the Red Sea is not going to lead us to exact answers about the importance of the various mechanisms that might have led to its own generation. With regard to the older oceans, the search for causative mechanisms is even more difficult. More detailed studies of older oceans themselves will help, but when we come to the newer oceans, to aid in this interpretation, there are so few of them that it's exceedingly unlikely that we're going to be able to come to some sort of consensus model for it.